So we are moving towards thinking about everything as random, all of our events as random variables, thinking about all of our events as numbers. Um, and that means moving towards thinking about joint distributions of random variables. Done joint distributions in terms of thinking about events that have joint probabilities, the probability of the intersection, that is. All we're doing now is we're saying, well, let's think about those events being represented as numbers. So that the realizations are numbers so that we can calculate expected values and variances. In doing that, this is kind of where the managing complexity comes in. So I want to introduce some notation that we'll be using going forward that conventionally does get used for random variables, not so much for kind of the basics that we've been doing so far. So I want to talk about PMF notation, probability mass function is what that stands for. Since we're just kind of going over terms and things like that, I want to mention the term moments. And the one kind of new conceptual idea in this lesson is conditional independence. Okay, so what we're going toward is, as I said, sort of joint, a joint distribution. Joint lets us know that I'm thinking about the probability that X has this value and Y has that value. So just as we did before, when it's simple random variables, we can represent that with crosstabs. So we might be thinking about X taking values little x1 and little x2, and Y taking values little y1 and little y2. And then in here, we're going to have the probabilities. Okay, so didn't leave myself much space there, which is actually okay because I want to go outside here. What we would typically put here using our old notation would be the probability of the joint event that random variable X takes value x1 and random variable Y takes value y1. At this point, for the sake of this Zekless, most books, most teachers, including me, switch out of this kind of set-based notation, thinking of that's sort of emphasizing the fact that we're thinking of events as sets, and into outcome-based notation. And when we do that, we can think about this, we can think more explicitly about the fact that this probability is a function that is assigning values to joint realizations. And in this case, our joint realizations are numbers. So we really are thinking about a probability function that is taking numbers like x1 and y1 and assigning a probability to them. And so we're just going to rewrite that as p, so lowercase p. I'll just write the whole thing, uppercase xy in the subscript x1, y1. Okay, so it means the same thing as that. This we would call the probability mass function. So like I say, it's the function that takes values for random variable X and random variable Y and assigns them probabilities. Okay, so it could be X1, it could be the probability X1, Y2, X2, Y1, etc. We'll get to some examples of putting specific values for the argument of that function. What we've got down here in the subscripts, and there's going to be kind of a lot of action in the subscripts coming up, is it's telling us which PMF it is. So this is telling us that we have the the joint PMF. Okay, that we might distinguish, for example, from the just the marginal PMF of X. Okay. Or getting a little bit ahead, something like the conditional, the PMF of X conditional on some event A here. Okay. So what's going on in the subscript here is it's telling us which function we're talking about, and what's going on here is which values we're talking about. You don't necessarily put all the stuff in every time you write these things. Working with PMFs in these kinds of situations, there's always kind of this trade-off between being really redundant and sort of seems like you're writing too much, or being too terse to the point where you can't really tell what you're talking about. And sometimes context will let you know. So for example, sometimes if I was really sort of concerned that people might misinterpret what I was saying, I might write this as PXY random variable X equals X1 random variable Y1. Or I might write this as probability of X conditional on A, X equals X1, even having the conditional on A. Okay, so yes, this is kind of redundant here, but sometimes, as I say, this, especially when you substitute specific numbers in there, can sometimes be too terse. So I'm just alerting you that this notation is, shall we say, flexible. In general, when you have options about how much detail to go into in your notation, it's never a bad idea to err on the side of a little bit of redundancy. A little bit of redundancy is easier to tolerate than any amount of genuine confusion. Okay. So again, the extra information that's coming in by using this PMF notation is we're using subscripts to indicate, are we talking about a joint probability function, a marginal, a conditional, those kinds of combinations. And so these tend to be uppercase and referring to the random variables themselves. What's inside the parentheses are the specific values. Okay, so this X1 would be a particular value that X could take. Y1 would be a particular value. So maybe just giving myself a little more space here to write the whole joint distribution here, that we would have X taking value X1, X2, and Y taking values Y1, Y2. This would happen if I'm doing cross tabs, putting the probabilities here in the cells. This would be the joint probability XY of X1, Y1. This would be the same probability function, but now we're looking at the values associated with X1 and Y2. Same probability function, the joint distribution of X and Y, but now we're looking at the probability that X is X2 and Y is Y1. And finally, same probability mass function, probability of X2, Y2. One last thing before I leave the topic of PMFs. The whole business with calling it a mass function, it just tells us that we are assigning probabilities to specific outcomes here. Okay, that random variable X takes this particular numeric value. And we are doing that when we have discrete values that the random variable can take. Looking ahead in a few weeks when we're going to be talking about random variable that's assigned over the whole real line and it has a continuous set of values, we're not going to be able to assign probability mass to individual points, and so we're going to call it a probability density function. Okay, so for the meantime, if you find yourself bothered by this M here, if you want to think about it as a reminder that this is letting us know that it's a random variable where we can count the realizations. They're not densely packed in the way numbers are on a real line. Okay, so fine, that's first thing I wanted to do, talk about PMF notation. I'm going to be using it going forward. Next thing, well, we're just defining terms here. I keep saying over and over again, mean and variance, conditional mean and variance, unconditional mean and variance. We use the term moments to refer to means and variances. So let's just write that here. I say moments, the function that mean, the mean and the variance. So pretty quickly, you'll hear me referring to things like conditional moments, unconditional moments. There, let's calculate the moments of a function. It just means mean and variance. If we want to be super precise about it, the moments are the expected values of x minus its expected value raised to successively higher powers. So variance would be the second moment. There are higher moments. The difference between x, the expected value of the difference between x at its mean raised to the power 3 is a moment called the skewness of a probability mass function. The fourth moment, that same thing, x minus its expected value raised to the power 4, and then take the expected value of that. That's the fourth moment, kurtosis. Those are things, they do have some interpretation. They're just not part of what we're doing here in 200A. So all I'm doing here in introducing this term is giving us all permission to abbreviate expected value and variance as moments. And usually that is what people mean by moments, the first two moments. First moment being expected value, second moment being variance. And the use of that word is an analogy to the way the term gets used in physics and like calculating center of mass and things like that. Not super helpful. I guess if you see the analogy right away, that might be helpful. I don't think it's worth learning the analogy to physics to understand the probability meaning. All right, so PMF notation, we talked about what moments mean. The one sort of new idea I want to talk about here is conditional independence. So let's go to a new page for that. Okay, and actually before I talk about conditional independence, let's just talk about independence in the context of random variables using the PMF notation to sort of remind ourselves of what independence means. Okay, so sort of regular independence here. So if we say that random variable x is independent of event A, and let me maybe emphasize that this is an RV, this is an event. What are we saying there? That just means that the conditional probability that random variable x equals value x1 is the same as the unconditional probability that x equals x1. Okay, so this is just what it's I'm just using the new PMF notation to say what we've always said about independence. Okay, that if x and a are independent, then learning that a is true doesn't affect our beliefs about whether x is true or not. And that goes through when both our events are random variables. Okay, so if x and y are independent random variables here, what that just means is that the probability of x conditional on y, okay, so I might write that as x equals little x conditional on y equals some value is just the same as the unconditional probability of x. on the redundant side there, but very clear what I'm talking about. And saying this in words is what we've always thought about independence, is that if X and Y are independent random variables, learning the value that Y takes, learning how Y came out, doesn't change our beliefs about how X came out. All right, so that's plain old independence. Let's have a new color here. Let's put a little black. I haven't used black yet for conditional independence. So I'm going to talk about two random variables, X and Y, are conditionally independent if probability of X conditional on A and Y. And let me be not so terse with my notation. The conditional probability of X conditional on A. So I'm having A being an event here and Y being realization of a random variable. It actually works if they're both random variables or even if they're both events. But A and Y equals Y is just the same as the probability of X conditional on A by itself. All right. So what this is saying is that X and Y are independent conditional on A, and that's actually important enough that I think I want to write that here. Are independent conditional on A, because it's always like, what is the event that's creating the conditionality here? So they are independent conditional on A if, given that we know A, so we know A on both sides of this, given that we know A, learning Y, learning how Y came out, that Y took a specific value, doesn't change our beliefs about A. Okay. So where we're going with this is we'll be thinking about another election and assuming that if we know there's anti-incumbent sentiment, the outcome of that election is independent of the outcome on the city council election, okay, which might be plausible. It's not the same thing as assuming that the two elections unconditionally are independent, okay? So the whole idea is that thinking about what other things that we might know, other things we might be conditioning on. Do we know whether we're in the world of A or do we know whether we're in the world of not A, determines whether a pair of random variables is independent of each other. That's the whole lesson to sort that out. I'm just giving you a preview here. The one last thing I'll say about conditional independence, that it's true for any kind of independence, but and follows directly from this is if X and Y are conditionally independent, then we can find the joint probability conditional on the event that makes them independent, okay, conditional on A. Sorry, did I do that right? That's the other problem when you have too much redundancy in your notation. It's honestly easier to make mistakes here, but it's the conditional, the joint probability of X and Y conditional on A. Okay, so it's both joint and conditional here. Joint because we're thinking about X and Y, but conditioning on some other event here. And that's the probability that random variable x takes value x1, random variable y takes value y1. If they are conditionally independent, we can get that joint probability by multiplying the two single probabilities. If they're not independent, we can't do that. One of the big lessons of 200A, if they're not independent, you can't just multiply the marginals. But if they are independent, or if they are conditionally independent, you can get the conditional joint probability by multiplying the probability that x equals x1 conditional on A times the probability that y equals y1 conditional. Okay. So we might be in a world where assuming independence is implausible, ridiculous, we don't want to do it. But if we can model that world in a way of thinking about possible subcases where x and y would be conditionally independent, then we can find their joint distributions by multiplying the marginals, and that turns out to be super convenient. Okay, so that is where we're going in the next lesson, and where hopefully an extended example will clarify what we're doing. So I'll see you then.